Hello, sir. Welcome to the podcast. It's an honor having you here.
Thank you. It's a great pleasure to be talking to you as well.
To begin with, considering your vast experience in the quantum domain, could you share your current primary area of research and what you're most focused on right now?
The focus now is on testing quantum effects in the macroscopic domain. So this is actually a very important question in science, namely whether there is a limitation to the laws of quantum mechanics. Do they only hold in the microscopic domain? When we are talking about simple systems like particles of light or atoms or simple molecules, or is it possible really that all of these quantum effects persist even in complex systems like chemical reactions, biological systems? And of course, for a physicist, I guess the biggest outstanding question is gravity. Gravity and quantum mechanics act on completely different domains, and trying to come up with experiments to test the physics where both gravity and quantum mechanics matter is probably one of the hottest topics in physics at present.
Right, sir. So it's amazing. So, what initially motivated for you to pursue a career in physics?
It's a good question. Um, round about probably my high school, when I was 16, 15, 16, 17. Um, it's probably my first proper exposure to physics. There was no quantum physics at that time. And even later in my high school, when I was 18, I think this was taught in a very superficial way. At best, you would learn something about old quantum theory, maybe what Einstein and Planck did or Niels Bohr did, but there was certainly no proper quantum mechanics. So what made me really somehow fascinated by physics was I think it was a lecture by one of my teachers. This was a teacher I think I only had that one year. They almost changed on a yearly basis, and most of my physics teachers I didn't really like, which is interesting as well. But this teacher showed us how to derive the equation for a simple ideal gas. So the pressure times volume is proportional to the temperature, basically, is the relationship. And it's probably one of the most relevant relationships in thermodynamics, which governs macroscopic systems, large systems, many collections of many atoms. What she showed us is a very simple argument. I think it goes back to Bernoulli. I later realized how this was done historically. She showed us a simple way how to start from Newton's laws, which govern everything basically in classical mechanics, including atoms at that time. That was thought that they are governed by Newton's laws. And she showed us how to start with this microscopic description and in a very few simple steps with a few assumptions to derive this law of thermodynamics. And I thought this is amazing that physics actually doesn't just explain phenomena in one particular narrow domain, but these laws that come up in a very simple set of experiments do actually apply to the macroscopic domain. And I think that made me ultimately confident. This is, I think, why probably most physicists like myself are what philosophers would call reductionists. So what that means is that people like me believe that everything ultimately should be, hopefully, we don't know, but it should be hopefully understood in terms of the basic microscopic laws of physics. And this was an extremely powerful thing. And I think from then on, um, I really very quickly, probably during that academic year, I realized that I want to study physics. I was already good at maths. I think maths was relatively easy for me, which helps if you want to be a physicist. I didn't like chemistry. Chemistry wasn't my thing. Only now I'm going back to chemistry when I understand it really from the very foundations of quantum mechanics. And it's an amazing subject, obviously, but somehow it wasn't maybe taught or I didn't understand it properly as a student. So I think it was already in my high school. And then later on, I never really questioned this. I think the more I learned about it, certainly the deeper this mystery became, and the kind of profound awe that one has for the beauty of natural laws. But I think quantum mechanics I only properly met as an undergraduate in London at the Imperial College. I think it was taught in the first year. And then I realized that there are so many more actually counterintuitive facts about physics. And at that point, it was clear to me that that's what I want to do, really.
That's a really nice story, sir. And talking about quantum gravity, what is the current state of resolving it? Have there been any significant breakthroughs in the recent years?
Yeah, it's a good question because I think we have a multitude of theories, and they all follow different philosophies, really. There are even theories that claim that you will never have to quantize gravity and you will somehow have to consistently put it together with quantum mechanics that's obeyed by the rest of the universe, other forces, and everything else. I'm not very sympathetic to this view, but there are theories of this kind. On the quantum gravity side, if you engage in quantizing gravity, there are also many possible views. And the reason is that we don't really know. We have zero experimental input as to what exactly should we be quantizing when it comes to gravity. So one obvious idea, for instance, is to say, well, gravity is really, Einstein's theory says that gravity is some kind of curvature, bending of space and time. And so if you want to address this quantum mechanically, some people would argue that you need to quantize space and time. And there are many theories of this kind. Loop quantum gravity is one of them. There is non-commuting geometry, many approaches to
String
this.
theory.
String theory indeed is another possible direction. Then you have, all of these canonical approaches, as people call them. They say, just think of different gravitational fields. So in Einstein's theory, there are 10 different gravities instead of just one, as in Newton's. You have 10 different potentials. And people say, well, for Einstein, they're just classical entities. But what we should do is upgrade them into quantum entities, make each of them an operator, and that would be what one would call canonical, like the standard way of every other field is quantized exactly this way. And this gives you something different to quantizing space-time directly. But like I said, we have no way of distinguishing between the two. So what I did a few years back with Chiara Malletto and independently, a colleague and a friend of mine, Sugato Bose from UCL, University College in London, what we did is we proposed a test to simply see whether any components of gravity are quantum mechanical. So it doesn't discriminate how we should quantize it, but it's designed to test whether gravity could remain classical or it really needs to be quantized. And if our test is successful, it hasn't been implemented yet in any laboratory. There are 5 or 6 laboratories now racing to do it. But if it's successful the way that we anticipated, I think it would rule out the semi-classical description as it's known. The description where everything other than gravity is quantum mechanical and gravity is classical. This would be inconsistent, I think. And this would be a big breakthrough. It would at least eliminate half of the possible theories. Anyone who, for instance, advocates collapse of quantum mechanics due to gravity, this kind of theory would fail this experiment ultimately. So it would kind of eliminate, maybe this is not completely accurate, but let's say eliminate half of the approaches to quantum gravity would be gone. But the other half of approaches, as you mentioned, string theory, loop quantum gravity, any canonical approach, they would all um, pass this test. And I think what I'm thinking about now, more specifically, is how do I discriminate these different quantum approaches to gravity? All of them are genuinely quantum, but what they advocate is that the fundamental entities that become quantum are completely different in each of these theories. And actually, no one knows how to test this. This sounds very much beyond the current state of the art, but you never know. The more you think about these things and the more the technology progresses, we might be able to get there too.
That's nice, sir. And I'd like to get your opinion on the rapid advancement of artificial intelligence and its role in solving complex scientific problems. And I
Yes.
also would love to know if you incorporate AI in your research.
Good question. Actually, in my research, not fundamentally, in the sense of looking for problems to do. I think this is still something that humans are much better at, and it's not easy to see whether or how quickly this could be substituted by AI. But AI is an incredible actually help in searching for references, compiling things, even writing, collecting your references, writing bits of the text. It's a phenomenal tool. Actually, it's extremely advanced. If you are, of course, asking more complex questions, like solving physics problems, then you really need to be careful, obviously. I think you need to double check all the answers. I know that even when I set my exam questions for undergraduates, I know that AI is frequently incapable of solving lots of these questions. So I think you have to take it with a pinch of salt. However, and I think this is an important point. Um, I think I've always been what you would call a strong AI supporter. So what I mean by strong AI is that um, if you really think that what our brain does is simply utilizes the underlying physics, and it's all really about physical processes which support some kind of information processing. If you believe that that's all there is to our brain, including consciousness and all other facts that are linked to it, then I see no reason why we shouldn't be able to replicate this artificially. What we
Mhm.
have currently doesn't do the job, and it doesn't do the job
Right.
for the simple reason I think that we have no idea how the brain works. We actually don't have a single good model for how our brain works. But I think this is a hugely exciting research area. What AI did change, it seems to me, so it wouldn't have changed, it would probably just strengthen beliefs of people like myself who already thought that computationally we can probably replicate even consciousness ultimately. But the people who didn't believe this, it seems to me that a number of people like that has now changed their mind simply because of the rapid progress. Once you witness what AI is capable of doing, even currently, I think you have to start to question some of these assumptions if you really think that consciousness is something special and it's beyond computation and things like that. So I think the main value is in that. And no doubt it will become even more valuable in research as time goes on.
That's nice, sir. I recall seeing one of the conversations between OpenAI CEO Sam Altman and David Dash, where Sam Altman has asked David Dash if one day AGI, like GPT-8, would come and solve quantum gravity, would David Dash completely accept AI supremacy? To which he replied in affirmative. So, what do you think? One day, a very far advanced model like GPT-8 or some AGI system could solve quantum gravity?
Yes, actually, I would be impressed with much less than that. Certainly, again, with all of the caveats that we already discussed, in the sense that I don't think this solution would be of the form as a new mathematical theory of quantum gravity, because, like I said, what we are lacking is really experiments to test which of these approaches are the ultimately are the relevant ones. What would be in this period, what would really be impressive already is if AI could, in fact, think about even thought experiments that would discriminate some of these approaches to gravity. So I would already be impressed with that, even without providing ultimately the full theory of quantum gravity. But even reproducing other laws of physics that we are already familiar with. That's something that, like I said, AI cannot do. Like it's struggling even with some undergraduate physics questions. So to me, already being able to solve some of these things, and even more importantly, to really explain to you rather than just spitting out a
Hmm.
solution and not saying anything, if he could engage in a dialogue, how we people really convince other scientists, for instance, that our ideas are valid. Then I would certainly say that this qualifies for let's say for information processing capabilities that are very comparable to the human brain. Of course, we don't know whether the nitty-gritty are exactly the same, and this would require a lot more further study. But it could happen. GPT 8 or 10, I have no idea. It is not impossible.
Well, that's a very nice, unique perspective, sir. And you also work in foundational quantum mechanics, and many people who want to work in foundational quantum mechanics have this opinion that that is complete. Like there is nothing much really big to explore. We will be in a career crisis and something like that. So, what do you have an opinion for that?
Yes, I think it's important. I'll tell you why. Because this has been said by many people, and I think physicists physicists are usually, I think, all good physicists, I would say, um, must be familiar with a multitude of different ways in which one problem, let's say if we're talking about quantum mechanics, can be solved. So I think all of us are usually familiar with almost all the, let's say, five, six, seven major interpretations. And we can
Mhm.
tell the story, even though the calculations may look very similar, the story that they communicate are actually very different. They're different accounts of what's going on in one and the same experiment, even though you might be predicting exactly the same number ultimately. So this is why sometimes people say, well, these are just interpretations. So it's true that even if you cannot discriminate them at present, what matters for interpretations are two things. One is that when you encounter a new problem, one of these ways of thinking about it will turn out to be more fruitful than others. And that's what's interesting. Um, you'd be surprised how even switching from the Schrödinger way of doing quantum mechanics to the Heisenberg way of doing quantum mechanics can solve certain problems much faster. So already switching these two interpretations, which we know are actually equivalent, two equivalent ways of calculating one and the same probability ultimately. In fact, if you follow one way, you will get there much faster than if you follow the other way. So that's one reason, just simply pragmatism, and that's why being aware of all of these different ways is extremely helpful, because you never know which of them is going to give you a faster way of understanding something. But the much more important point is that we don't know which of these ways will be the one that will lead us to a new theory. So I think most physicists, again, wouldn't be surprised if quantizing gravity gave us a completely new theory of physics. It's something that reduces to gravity in the special limit, reduces to quantum mechanics in another special limit, a bit like string theory again that you mentioned. However, together, taken together, it's a really genuinely different theory. Now, it could well be that one of the interpretations of quantum mechanics, it's much closer to kind of working and coming up with the basic rules of this theory than other interpretations. And we already have a historical example for this. Classical mechanics, it turned out that Hamilton's way of doing there are three ways of doing classical mechanics, very crudely speaking. One is due to Newton, the original way. Then Lagrange came up and did something ingenious. And then Hamilton came up and did something even more ingenious. But all of them agreed with Newton. There was no deviation. It was still the same classical mechanics, but phrased very differently.
Right.
And Hamilton's version, which would just be an interpretation in classical times, is actually the one that led Schrödinger to write the Schrödinger equation. Ultimately, it's all about the energy of the system, and it's not about forces and things like that. So we didn't know that before, and someone could have also asked Hamilton, why do you worry about the foundations of classical mechanics? You know, it gives you exactly the same results as Newton. But actually, 50 years down the line, it turns out that his approach was instrumental. And it seems to me that one of these interpretations of quantum mechanics will be better than others when we're thinking and working on our new theory.
It's nice. You have written many popular books. One of them is The Decoding Reality. And I also wanted to know more about the current book which you're writing.
Yes, yes. Yes, I've written three popular books. The current one is really fresh. It was just published a month and a bit ago, 2 months ago, and it talks exactly. It's called Portals to a New Reality. So what I was imagining exactly is a set of 5 experiments. They are defined very broadly, which I think we should be focusing on in order to probe the validity of quantum mechanics in the macroscopic domain, and also in order to have a chance um, to see a new theory, to really come up with a new theory in physics. And I argued in that book that technologically we've now reached a level where we can actually start to think about these experiments. Um, and I try to predict that within the next decade, maybe even less, we will already have this first indication, for instance, of whether gravity is quantum mechanical. So that's certainly one of the portals that I discuss in the book. But I discuss a lot the notion of observation in quantum mechanics. I talk about artificial intelligence and computers being observers and testing this within a very complicated quantum mechanical setup. I talk about the role of quantum mechanics in chemistry and biology and things like that. So the book is written mainly to counter a number of these views when people say that physics is stuck and we haven't had a new theory for a long time and it's boring and so on. I actually felt very differently, and I feel very differently about these things. And I actually think that we are very close to a new revolution in physics. And that's what prompted me to write the book, to communicate this.
That's nice. Is there any new concept or something new you explored or some new insight that struck you when you were writing the book?
When I was writing the book, what was interesting, yes, I actually dug around quite a bit in various directions. Things that surprise me a lot always are bits that you find out in biology, because it's not my field, but there is a tremendous amount of progress in actually testing quantum phenomena in biology. And one always gets surprised because biological systems are extremely messy. They're complex. They operate at room temperature, very high temperature. And of course, in physics, we know that if we want to test the full quantum behavior, we need to control our system very well. It needs to be a relatively simple system. It should certainly not be vibrating a lot at high temperature. Usually, we have to cool systems down to very low temperatures, millikelvin, sometimes a billionth of Kelvin, to get things like Bose condensates and so on. So if someone says, "Oh, look, I've got biological systems that are also behaving quantum mechanically," to me, this is actually usually a huge surprise. And it makes you wonder, it really does make you wonder actually, how many of these effects are relevant for some key functions in biology. So we keep discovering this in photosynthesis, in the mitochondria. There are some speculations that even the ways that our cells generate energy, the mitochondria is like the powerhouse of the cell, that even some of these processes rely on quantum transport of energy, of
Mhm.
electrons, and so on. So to me, I think the future of biology is going to be extremely exciting because we're going to be going more and more into this microscopic domain to really try to understand everything in terms of quantum mechanics. But that was just one surprise. There were many others. I think I was surprised even on the side of quantum mechanics as I was reading deeper about some different views of quantum mechanics. Some of the things on artificial intelligence side as well. As we discussed, the progress is tremendous, really. And it's not at all excluded that we will be developing quantum artificial intelligence, for instance,
Mhm.
relatively soon. People are already talking about it. Small tasks within conventional classical AI could already be done quantum mechanically.
Mhm.
And it just makes you wonder how much more powerful this entity would be if you really treated it quantum mechanically.
Speaking of which, I wanted to also ask you about quantum computing, that also being one of your areas of research. Industry
Yes.
leaders like Google and Microsoft claim that the future of quantum computing lies where once AI was 5 years ago. So I want to know how close are we to get commercially available quantum computers and how that can completely change the paradigm of computing.
Excellent question. It's again from about 2000 onwards. And I think what happened, I can even tell you what prompted all of this. In the late 90s, there was still a debate whether, for instance, mesoscopic systems like superconductors could really exhibit the full range of quantum behavior. So, can you make a proper quantum bit, even a single quantum bit, which means that you can prepare it in any quantum superposition that you like? Can you get a superconductor to really support a full quantum bit? At that time, there were many people, some of them prominent physicists who even had Nobel Prizes. They were actually arguing that you will never be able to do this with a superconductor. And then in 98, 99, a couple of experiments came up that actually demonstrated that you can make quantum bits with superconductors and you can even entangle two quantum bits. It was a beautiful experiment by Nakamura, a Japanese physicist who did that. And I think from then on, it became clear that actually superconductors are one viable way to making quantum computers. And this was exciting because remember, the computing industry is all about semiconductors, and it's much easier to integrate these kind of systems like superconductors than, for instance, single atoms as qubits, which also people are developing. And I like that approach a great deal, actually, as a physicist. But it's very difficult to see how you could incorporate that with the rest of the solid state architecture that we have in our conventional computers. So I think from about 2000 onwards, there was a rapid investment into superconducting qubits, and of course, along the way into other qubits. And then about 2010 onwards, heavy industry started to get involved. So we have Microsoft, Google, Amazon, almost anyone you can name now is developing quantum computers. And that's extremely important because they're not going to be made in an academic institution. Academic institutions don't have enough resources to actually do this. It's a very costly
Hmm.
enterprise. Having said all of these things about rapid developments, we're still not beyond, I would say, 100 quantum. If you want to talk about a genuine quantum computer in terms of universality. And so what that means is that you can execute whatever quantum transformation you want on this computer. You can prepare any quantum state, no matter how entangled it is. Then I think at present we do not have more than 100 qubits. And I think even that's optimistic. Some people are
Hmm.
announcing close to 100 and so on. I think in terms of high fidelity, we are still talking about 20, 30, so less than 50. However, the progress is rapid. And again, I wouldn't be surprised if within the next decade we do actually come very close, if not develop a full universal quantum computer. Already to beat a classical computer, if we had 1,000 genuine logical quantum bits, then we could already do phenomenal things that no classical computer can do. The tricky bit at the moment is that they are very noisy. So in order for you to have 1,000 logical qubits, you actually need 1 million physical qubits, as they call them. So
Right.
that's already much harder because you have to introduce a huge redundancy. For every single qubit, logically speaking, you need another 100 to 1,000 qubits to really protect this. So you're using 1,000 qubits only for one logical quantum bit. And error correction is being developed. And
Hmm.
ultimately, people believe that it will be necessary. However, that really is making the progress much harder. What would change it rapidly is, for instance, finding a more stable quantum bit at higher temperature than the ones that we use now. If we had room temperature superconductors, for instance, it would
Right.
eliminate any need, presumably, for error correction of this kind. And of course, then, it would be much easier to make a universal computer. So I'm optimistic that interesting things will happen within the next decade. I think what this would do for us is really tackle all of these complex problems that we are solving for which classical computers cannot give us any answers. So people talk frequently even about biomedical applications. Obviously, to us humans, these are the most interesting applications. Um, Discovering new drugs, simulating drugs on a quantum computer so we don't have to go through trial and error when we develop them, but we could actually develop them with the ab initio understanding of quantum mechanics and a direct simulation on a quantum computer. Other complex systems like predicting, weather patterns, anything in the real world actually is usually far too complicated to understand in detail with a classical computer. And so these are the problems that quantum computers could really help us with. And I believe even in this intermediate period, when we have
Hmm.
less
See,
than 100 or 1,000 qubits, we will still be able to use a hybrid architecture to speed things up. So they're going to be useful even in the current state of affairs.
that's nice, sir. And I wanted to know what are the key traits and qualities you look for when taking a PhD student?
Uh, so to me, what matters, I should say, yeah, that's an important question because different people approach this very differently. To me, I'm always looking for someone who is really curious and passionate about science in general, because I think what I do is very interdisciplinary. I've
Mm.
supervised mathematicians, computer scientists, chemists, even philosophers. Of course, most of my students are with a physics degree, but I've actually had students from many other um, fields who are just simply interested in quantum information and quantum computing. So it's a really multidisciplinary area. So I'm looking for curiosity and independence, um, in the sense that I think a PhD is really meant to be your own work, where you have to come up ultimately with your own ideas as well as solve these ideas. So I discuss many problems with students at the beginning, but I don't I don't force my students to join my own research and do some small parts of my own research,
Mm.
which is how it works in many, especially experimental directions. I really expect them to develop their own ideas, and to follow their own intuition, even if it goes contrary to my own beliefs and intuitions. I think that's extremely important because it's difficult to get any progress if everyone just follows what people before them have done. So to me, curiosity, passion, independence are really the key features. The background, like I said, is not that important because I think if you are curious and if you are passionate and if you like the topic, you will learn ultimately whatever it is that you need to learn. I can give you an example. One of my best students actually came from an undergraduate degree where he studied oceanography.
Mm.
So this is a degree for environmental science, actually. There was virtually no quantum mechanics until he did his master's degree. And during the master's degree, I gave a very short set of lectures on quantum mechanics, I think three or four, a handful of lectures. And he approached me immediately and he said to me, I loved what you just told us. Can I do a project with you? And could I then come and do a PhD with you? And I looked at him and I said to him, I don't know if you can. What do you think? Can you do it? And actually, it was clear that he loved this challenge. It was immediately clear that he was extremely curious about this. We did a 6 months long project as part of his master's, and then I took him immediately as a PhD student. So the fact that he never did much quantum mechanics formally for his undergraduate degree was really not relevant. Obviously, he was a physicist. He did a lot of relevant mathematics. So I was saying that this is one of my best examples where basically he came with very little knowledge of quantum mechanics. It was clear that he realized that he really likes the subject and there are many interesting things he wanted to research in. And I think when he did his research, it seemed relatively easy for him to acquire all of these skills at the beginning of his PhD, and I don't think that slowed him down at all. And he always worked on very interesting and adventurous topics. So I think that's why I think passion, curiosity, independence are much more important features than exactly, what courses did you attend as an undergraduate and things like that. I don't think it's very relevant, really.
Right, sir. And I keep asking this question to my guests. If there is something that you could go back in time and fix in your life, what would it be and why?
Many things, probably. Yeah. Well, as you know, I mean, it's of course easy to I think look at things backwards and to realize that you could have done many things differently. Um, Certainly, one thing with my own career and life in science would have been that that moment, for instance, when I realized that I really liked physics and that I wanted to probably dedicate much more time to that, I think I would have been better off um, being able to focus more at that time. So I think this is simply the way that education works. And I think in my case, it was very broad, even at that time. So I think it was a typical kind of continental style, like a baccalaureate, where you study all subjects, including all the humanities and literature and everything else. I think for me would have been much more beneficial to somehow go straight into some very simple problem solving exploratory research directions. And it seems to me now we are more alert to these possibilities. And when I look around, people encourage younger people to be more adventurous. There are even people offering sponsorships to 16 to 20-year-olds to really try to do
Mm.
things independently and go straight into research. I think I would have certainly liked if someone offered this opportunity to me. But of course, it's too late now to change any of these things.
What is one final advice which you have for all the students who are willing to pursue a career in science?
I think it's a great time to be a scientist. I could even link it to what you asked me about the AI. People are now frequently thinking, well, with these rapid developments of artificial intelligence, what kind of degrees give us kind of secure prospects for jobs in the future. And it seems to me that jobs that require the human kind of creativity, which is definitely lacking in artificial intelligence. And I think the best examples of these jobs are really scientific jobs, the
Hmm.
thinking that's required for coming up with new ideas, hypotheses, coming up with experiments, how to test them. I think these professions are not only exciting, and I think they're very fulfilling if you like this kind of thing. But it seems to me that they will also be secure in the light of these rapid AI developments, at least for a while. So I would say now is a fantastic time to focus on science and really go interdisciplinary. Try to connect the gaps that exist between sciences at present. Try to look at the connections between physics and chemistry, chemistry and biology, and even beyond biology and neuroscience. It seems to me that these are still relatively disconnected topics. And I think the future really lies in exploring the connections and seeing how you can set up these bridges, because ultimately, no scientist really would like to believe that reality is divided in this way. It must be more coherent, really.
Right, sir. So thank you, sir. We are done with the questions.
Thanks very much.
Um, it's my pleasure having you on board.
Thank you.
I hope you enjoyed all the questions.
Thanks very much. It was great. Yeah, I really enjoyed it.
Thank you, sir.